Hello everyone. Now it's time to discuss some numerical problems related to the centrifugal pumps. As a prerequisite, for a centrifugal pump, as all of us know, the discharge is radial at inlet. That means alpha equals to 90 degrees and hence VW1, velocity of whirl at inlet, would be equals to 0. The tangential velocities can be calculated with the help of diameter and speed. U1, the tangential velocity at inlet, is pi d1n by 60, and the tangential velocity at outlet, U2, is pi d2n by 60, where n is the speed of the impeller and d1 and d2 are the diameters. Work done by impeller on water per second, or work done per second, is calculated as W by G into VW2 U2. Make sure you do not have VW1 term here because VW1 is already 0. Further, work done by impeller on water per second per unit weight per second. So per unit weight per second is an extra part here, and that can be calculated as 1 by G into VW2 U2. The discharge can be calculated, and discharge is area into velocity from the concept of continuity equation, and that is also equals to pi d1 b1 into vf1 at inlet, and it is also true for outlet by saying pi d2 b2 vf2, where d1 and d2 are the diameters, b1 and b2 are the widths, and vf1 and vf2 are the velocity of flows at inlet and outlet respectively. For velocity, for discharge being constant, velocity of flow vf1 would be equals to vf2. Let us discuss some numerical problems. The problem statement is the internal and external diameters of the impeller of a centrifugal pump are 200 mm and 400 mm respectively. The pump is running at 1200 rpm. The vane angles of the impeller at inlet and outlet are 20 degrees and 30 degrees respectively. The water enters the impeller radially and velocity of flow is constant. Determine the work done by the impeller per unit weight of water. There are few data given along with the problem statement, such as diameters d1 and d2. Obviously, when it comes to a centrifugal pump, d1 would be always smaller than d2. So d1 is 200 mm or 0.2 meters. d2 is 400 mm or 0.4 meters. The pump is running at 1200 rpm, says n is given, n is 1200 rpm, and there are vane angles given, vane angle at inlet and vane angle at outlet. So vane angle at inlet is theta, which is 20 degrees, and vane angle at outlet is phi, and phi is 30 degrees. Water enters the impeller radially. The meaning of this statement is alpha equals to 90 degrees, and whenever we say alpha equals to 90 degrees, remind you VW1 equals to 0. And the velocity of flow is constant, that means Vf1 is equals to Vf2. And finally, we are supposed to calculate work done by the impeller per unit weight of water by using a very simple formula, which is equals to 1 by G into VW2 into U2. Now let us draw the velocity diagram, which is a very essential part of these kind of problems. The vane, the backward vane, at inlet V1, which is equals to Vf1, because alpha is equals to 90 degrees. However, it is not mentioned. U1, the tangential velocity, and the relative velocity is Vr1. Now alpha equals to 90 degrees and theta, the value is given as 20 degrees. Let us go to the outlet part. V2, the absolute velocity, and U2, this is how we draw U2, and the relative velocity Vr2, and the angle made by V2 with respect to U2 is beta. One more angle, beta, and phi is the vane angle at outlet, and the component of V2 vertically across the direction is Vf2, and VW2 is along the direction or parallel or horizontally is VW2. Now let us try to write the data given. D1 is given as 0.2 meters, D2 0.4 meters, and the speed n is 1200 rpm. We have some more data such as vane angle at inlet theta 20 degrees, vane angle at outlet phi 30 degrees, and alpha is 90 degrees obviously, and that's how we say VW1 equals to 0. Okay, and the problem statement says velocity of flow is constant. That means Vf1 equals to Vf2. The tangential velocity of impeller at inlet and outlet can be calculated. U1 and U2 can be calculated with the help of D1n and D2n. How? So U1 is pi D1n by 60, and even U2 is also equals to pi D2n by 60. By substituting the values of D1 and D2, very easily we can calculate U1 and U2 in terms of meter per second. So U1 is pi into D1 is 0.2 into 1200 by 60, whereas U2 is pi into 0.4 into 1200 by 60. Here we have the values of U1 and U2 as 12.56 meter per second and 25.13 meter per second. Now here you can use a thumb rule. When it comes to a centrifugal pump, as D1 is less than D2, U1 should be less than U2 always, or U2 should be always greater than U1. Okay, let us go to the inlet velocity triangle. In the inlet velocity triangle, for a given value of theta, you can write tan theta equals to Vf1 by U1. Vf1 is nothing but V1. So it's Vf1 divided by U1. Now here the value of theta is given and Vf1 is unknown. So Vf1 can be calculated as tan theta into 12.56, or Vf1 is 12.56 tan theta, or further theta is 20 degrees, Vf1 is 4.57 meter per second. Now we know one more thing here. What is that? Vf1 is equals to Vf2. So Vf2 at the outlet velocity triangle is 4.57 meter per second. Why? The velocity of flow is constant here. Let's just go to the outlet velocity triangle. From the outlet velocity triangle, what is tan phi? Let us consider this right angle triangle. Now the tan phi is Vf2 divided by this end, this edge. So it's U2 minus Vw2. So tan phi is Vf2 divided by U2 minus Vw2, which is evident here. And that is also equals to, what is Vf2? From the earlier calculations, it is 4.57 divided by 25.13 is U2, and however Vw2 is unknown here, but we know the value of phi here. So we simplify for phi, we solve the equation for phi here, rather phi is known, we simplify the value for Vw2, and Vw2 is equals to 25.13 minus 7.915, and the value of Vw2 which can be calculated is 17.2 meter per second. Moment you calculate Vw2, we can easily calculate work done by the impeller per unit weight of water, and that is equals to 1 by G into Vw2 U2. So by substituting the values of Vw2 and U2 into 1 by G, the value of work done by the impeller per unit weight of water comes to be around 44.1 Newton meter per Newton. So whenever you calculate work done per second, the unit would be Newton meter per second, and the unit of work done per unit weight of water would be always Newton meter per Newton. So just to summarize, we calculated U1 and U2, and then we calculated Vf1, because Vf1 equals to Vf2. That's how we can proceed from the inlet velocity triangle to the outlet velocity triangle. And anyhow, theta and phi were given in the problem statement as a data. So Vw2 was calculated, and U2, along with the value of U2, we just calculated work done by the impeller per unit weight of water. Let us proceed with one more, a very simple numerical problem. The problem statement here comes: a centrifugal pump is to discharge 0.118 meter cube per second at a speed of 1450 RPM against a head of 25 meters. The impeller diameter is 250 millimeters, its width at outlet is 50 millimeters, and manometric efficiency is 75%. Determine the vane angle at the outer periphery of the impeller. The problem is very simple, provided you perfectly understand the given data. Let us revisit the problem statement once again. A centrifugal pump is to discharge, Q is given. Value of Q, the discharge is 0.118 meter cube per second. So we have a beautiful formula to calculate discharge, or a formula which is associated with discharge. Q equals to pi D1 B1 VF1. Okay, and that is also equals to pi D2 B2 VF2. And N is 1450 RPM against a head of 25 meters. H is given as 25 meters. The impeller diameter is 250 millimeters. Still, we are in a dilemma whether to go with D1 or D2. But the next statement says its width at outlet is 50 mm. So the width at outlet is 50 millimeters. B2 is 50 mm. So you can directly go with the value of diameter as D2. D2 250 millimeters or 0.25 meters, and B2 being 50 millimeters, 0.05 meters, and manometric efficiency is 75%. Let us proceed with the drawing of velocity triangles. The vane, backward vane, V1, which is also equals to VF1, and U1. Angle alpha is 90 degrees, and theta. The relative velocity VR1, at outlet it's V2, U2, and then the relative velocity VR2, the angle made by V2 with respect to U2 is beta, the vane angle phi, the component of V2, VF2, and the horizontal component is VW2. Let us list out the data given. Discharge Q is given as 0.118 meter cube per second. Speed N equals to 1450 RPM, and head HM, we just considered this as a manometric head. HM equals to 25 meters. The diameter at outlet D2 is given 0.25 meters. Along with the B2, the value of width at outlet is 0.05 meters, and the manometric efficiency is 75% or 0.75. The quest is to calculate phi. What is the value of phi? So is it possible to calculate the value of U2? Yes, it is. U2 is pi D2N by 60, D2 is 0.25, and N is 1450. Easily we can calculate the value of U2, and that is around 18.98 meter per second. Yes. What is the next step? Q is given here, the discharge is given, and the formula which is always associated with the Q is this. Q is pi D2 B2 into VF2. So in this formula, by substituting the value of Q D2 B2, in turn we calculate VF2. VF2 is velocity of flow. So VF2 is Q divided by pi D2 B2, or Q is 0.118 divided by pi into 0.25 into 0.05 being the values of D2 and B2. VF2 is around 3 meter per second. VF2 is 3 meter per second. Moment we have the value of VF2, so we also have some data related to the efficiency. Manometric efficiency is GHM divided by VW2 U2. Manometric efficiency is around 0.75 or 75%. And here we also know the value of HM. HM is the manometric head, and we calculated already the value of U2. So by using this formula, it's our job to calculate VW2 now. And VW2 is, if I rearrange this formula, it's VW2 equals to GHM divided by efficiency into U2. However, we know the value of HM, U2, VW2 is still the unknown, so we calculate here. So it's 9.81 into 25 being HM, and manometric efficiency as 75% or 0.75 into U2, 18.98. So the value of VW2 calculated is 17.23 meter per second. We have the value of VW2 now. We have already calculated VF2. Now let's just go to the outlet velocity triangle. In the outlet velocity triangle, from this right angle triangle, we know the value of U2 and VW2 and VF2. So easily I can calculate this edge, and this edge is U2 minus VW2, and this is VF2, and easily one can go with the trigonometric ratio tan phi. So tan phi is VF2 divided by U2 minus VW2, and if you just take the inverse, tan inverse, one can directly get the value of phi. So tan phi is Vf2 divided by U2 minus Vw2. Here these three terms are known from the previous calculations. So the tan phi is 1.7143, or if you just take the inverse, tan inverse of 1.71 will directly yield the value of phi, and that is around 59.74 degrees. So phi was the unknown, and that was the thing which we were supposed to calculate. I hope you have understood this. Let us proceed with one more problem. The problem statement is a centrifugal pump having outer diameter equals to 2 times the inner diameter and running at 1000 rpm, and it works against a total head of 40 meters. The velocity of flow through the impeller is constant and equals to 2.5 meter per second. The vanes are set back at an angle of 40 degrees at outlet. If the outer diameter of the impeller is 500 mm and width at outlet is 50 mm, determine vane angle at inlet, work done by impeller on water per second, and manometric efficiency. There are three things to be determined here. For a centrifugal pump, there is a relation given. The relation is with respect to the diameters. The outer diameter is equals to 2 times the inner diameter. That means outer diameter is D2 is equals to 2 times the inner diameter. Now the moment you have the outer diameter, the diameter of the impeller is 500 and width at outlet is 50 mm. That means D2 is given. So by using this relation, you can easily calculate the value of D1. And the N is 1000 rpm and works against a total head of 40 meters. Directly one can go with HM equals to 40 meters. The velocity of flow through the impeller is constant. That means Vf1 equals to Vf2, and Vf1 or Vf2, they are equal to 2.5 meter per second. The vanes are set back at an angle of 40 degrees. I hope this vanes being set back at an angle of 40 degree, it's a new thing for us. So let us discuss some more things related to this 40 degrees whenever we draw the velocity triangle. If the outer diameter of the impeller is 500 mm and width at outlet is 50 mm, we are supposed to calculate vane angle at inlet, theta, work done by impeller on water per second, and manometric efficiency. First, let us draw the velocity triangle. The backward vane at inlet V1 equals to Vf1, absolute velocity, and the tangential velocity U1, angle alpha, and the relative velocity VR1, alpha being 90 degrees and theta is the unknown here. When it comes to outlet V2, U2, the angle beta, and the relative velocity VR2 at outlet. Phi is the vane angle at outlet, Vf2 is the vertical component, and Vw2 anyhow the component of V2 in horizontal direction. Okay, so let us try to grab all the data related to this problem statement. N is given as 1000 rpm, Hm is 40 meters, and Vf1 equals to Vf2, which is equals to 2.5 meter per second. Now we have some secondary set of data here, phi being 40 degrees. The vanes are set back at an angle of 40 degree at outlet. This statement has ended with at outlet. So this angle is related to outlet. So you have a backward vane, and this vane is set back at an angle of 40 degree at outlet. So this is kind of a vane angle. So the vanes are set back. So this directly refers to the vane angle. So vane angle at outlet is phi. Phi is 40 degrees. D2 is 500 mm or 0.5 meters, and according to the very first statement, which says outer diameter is equals to 2 times the inner diameter. Okay, that means d2 equals to 2 times d1. Or how do we calculate d1? d1 is d2 by 2, and that's around 0.5 by 2 or 0.25 meters. And one more data which is given in terms of width at outlet is 50 millimeters or 0.05 meters. Let us proceed with the calculation part. We calculate the tangential velocities, and from the data we can calculate tangential velocity at inlet and outlet, because d1 d2 along with n are known. So u1 is pi d1 by 60, u2 is pi d2 n by 60. Let us calculate u1 and u2, both the values. So the values of u1 and u2 calculated are 13.09 meter per second and 26.18 meter per second respectively. Okay, so now we have the values of u1 and u2. Now let us go with the discharge value. So what is actually a discharge here? Discharge is pi d1 b1 vf1, which is also equals to pi d2 b2 vf2. Why we are not equating the discharge equals to pi d1 b1 vf1 is, except vf1 and d1 b1 is unknown here, and even discharge is also unknown. So d2 is known, b2 is known, vf2 is also known. Certainly we can calculate discharge here, and by substituting the values of d2, b2 and vf2, 0.5 meters, 0.05 meters and 2.5 meter per second respectively, one can easily calculate Q, and Q calculated is 0.1963 meter cube per second. Moment you calculate Q, we can also calculate inlet, the vane angle from the inlet velocity triangle. So from the inlet velocity triangle, theta is V1, which is equals to Vf1, and theta can be calculated as tan inverse of Vf1 by U1. Now the question is, how do we calculate Vf1? Vf1 can be calculated with the help of this Q. Q is also equals to pi d1 b1 Vf1, where except Vf1 everything is known. So tan theta is Vf1 by U1, and Vf1 is also known because Vf1 equals to Vf2. So it's 2.5. 2.5 by U1 is 13.09, and the value of tan theta is this, or theta is tan inverse of 0.191, and it is around 10.81 degrees. Okay, so we have calculated one of the unknowns now. Second one is work done by the impeller on water per second. It is just work done per second. Work done per second can be calculated as W by G into VW2 U2. But as of now, VW2 is unknown. First, let us calculate the value of VW2. So from the outlet velocity triangle, tan phi is, say, the tan phi here is Vf2 divided by U2 minus VW2. This edge is U2 minus VW2. The complete edge is U2, and out of this VW2 is this portion. So obviously the other distance becomes U2 minus VW2. So it's 2.5 divided by 26.18 minus VW2, where VW2 is unknown, but phi value is known. It's 40 degrees. So VW2, just by rearranging and substituting the value of phi equals to 40 degrees, VW2 calculated is around 23.2 meter per second. So the work done by impeller on water per second is W by G into VW2 U2. So what is W here? W is rho into G into Q, rho into G into Q, or gamma into Q by G into VW2 U2, VW2 U2. Rho into Q is mass per second, rho into Q is mass per second. So ultimately work done by impeller on water per second would be equals to rho Q into VW2 U2. You can cancel out GG here. So by substituting the value of VW2 and U2 here, VW2 being 23.2 meter per second and U2 is 26.18 meter per second, the work done by impeller on water per second is around 11 1,19,227.9 Newton meter per second. Of course, you can also express in terms of kilonewton meter per second. I hope you have understood all these numerical problems. Thank you.